I want you to close your eyes for a second. Imagine you are suspended in a fragile metal box, effectively a tin can, exactly 240,000 miles away from everything you have ever known. It is July 20th, 1969. The lunar surface is rushing up to meet you at thousands of miles per hour.
The eagle is descending. This is the moment.
Exactly. 3 minutes. That is all that separates Neil Armstrong and Buzz Aldrin from becoming the first humans to walk on another world or, becoming a permanent crater on the Sea of Tranquility.
And the tension in mission control is just suffocating. You can feel it in all the recordings.
And then, right at that razor's edge of history, the one thing keeping them alive, the guidance computer starts screaming.
And it wasn't just a warning light, not like a check engine light in your car. It was a full-blown go-no-go crisis. The alarms flashing were 12:01 and 12:02.
Right.
And here is the terrifying reality of that moment. For several heart-stopping seconds, nobody, not the astronauts and not the flight controllers staring at their screens in Houston, knew exactly what the computer was trying to tell them.
They had no idea.
They didn't know if the brain of the spacecraft was about to die.
And if the brain dies, the eagle crashes. It's as simple as that. The standard narrative here usually pivots to Neil Armstrong's piloting skills, which were, incredible, don't get me wrong.
Oh, absolutely, a legend.
Or the steely nerves of Gene Kranz in Houston. But that's not the story we are telling today. We are looking at the story that happened years before the launch. We are talking about the person whose logic was sitting inside that computer, making life or death decisions faster than any human brain could process.
We are talking about Margaret Hamilton. And while the name has gained some recognition recently, you might have seen that photo of her standing next to a stack of code listings as tall as she is.
It's an iconic photo.
It is, but I don't think most people grasp the technical magnitude of what she achieved. She didn't just, write code. She literally invented the discipline required to write it. She coined the term software engineering.
That is what gets me. Every single time. She gave the job its name. So the mission for this deep dive is to move past the Wikipedia summary. We are going to dig into the source material to understand how a student of philosophy, yes, philosophy ended up as the director of the software engineering division at the MIT Instrumentation Lab.
Right. And we need to understand the Wild West of 1960s computing because there were no rules, there were no textbooks, and there was no Stack Overflow to copy-paste from. You were on your own.
Yeah, you couldn't just Google the error message.
Not at all. And we are going to do a proper technical breakdown of the code itself. We need to unpack the asynchronous executive and the specific logic that saved Apollo 11. Because, and this isn't an exaggeration, without her specific approach to error prevention, the moon landing simply doesn't happen.
And we'll wrap up by looking at her career post-NASA, which I think is arguably even more relevant to us today.
Yeah.
She pivoted from how do we fix errors to how do we mathematically prove errors can't exist. It's a whole different mindset.
A total paradigm shift.
But let's start at the beginning. Margaret Hamilton, born 1936, Indiana-born, Michigan-raised. When we look at her college years, I don't see rocket scientist on the transcript. Not at all.
No, you see a really curious mix. She started at the University of Michigan in '55, then she transferred to Earlham College. She graduated in 1958 with a degree in mathematics.
Okay, so math is there. That makes sense.
Right. But if you look closer, there is a minor on that transcript that does a lot of heavy lifting later on.
Philosophy.
Philosophy. It feels like a distraction, doesn't it? If you're studying hard math, why spend time on abstract thought?
Well, she credits her father, who was a poet, and her grandfather, a headmaster, for that interest. But think about what philosophy actually is. It isn't just sitting around asking, why are we here?
Right.
It's the study of logic. It's the study of systems of thought. You learn how to construct an argument, how to find flaws in a logical chain. It's about abstraction.
So it's meta-thinking, thinking about how we think. Exactly. And when you are about to enter a field that doesn't exist yet, where there are no manuals and no established procedures, you can't rely on rote memorization. There's nothing to memorize.
There are no rules to follow.
You have to rely on systems thinking. You have to be able to look at a problem abstractly and derive the rules yourself. That philosophical background likely gave her the ability to see the architecture behind the code, not just the commands themselves. She could see the forest, not just the trees.
So she has the math, she has the logic, she graduates in '58. The plan was to be a professor, right? She was heading to Brandeis to study abstract math.
That was the plan. But, life intervened. Her husband was at Harvard Law School. They needed money to support him through that, so she put her own graduate studies on hold.
So she starts looking for work.
She starts looking for work, and she takes a job in mid-1959 at MIT. She landed in the meteorology department working for a man named Edward Norton Lorenz.
Okay, I recognize that name immediately. Lorenz is the chaos theory guy.
He is the father of chaos theory.
But wait, 1959. Chaos theory wasn't a thing yet, was it? That term comes later.
Not officially, no. And this is where the story gets so fascinating. Margaret was there at the incubation. She was tasked with writing software to predict weather on these massive, clunky machines, the LGP-30 and the PDP-1.
The LGP-30, I looked this up. It's the size of a desk, weighs 800 pounds, and probably had less computing power than a musical birthday card.
Oh, much, much less. And it was loud. And you had to feed it instructions on paper tape. It was a very physical process.
So what was she actually doing?
She was programming it to solve these huge sets of differential equations, trying to model weather patterns. They'd run these long simulations, printing out the results as they went.
And this is where the famous discovery happens.
This is it. One day, Lorenz wanted to rerun a simulation from the middle. So instead of starting from zero, he took a printout from halfway through, typed the numbers back into the computer, and set it running again.
And he expected to get the same results as the first run, just, from that point forward.
Of course. Same inputs, same math, should be the same outputs. But the result was completely different. The new simulation diverged wildly from the original.
Why? If the math is the same, the results should be the same.
You would think. But the computer, internally, stored numbers to 6 decimal places. The printer, to save paper and time, only printed out 3.
A rounding error.
A tiny, tiny rounding error. So when they typed the numbers back in, they were rounding off these microscopic fractions. Something like 0.506127 became just 0.506.
And that tiny difference changed the weather.
It changed everything. It completely diverged. This was the discovery of sensitive dependence on initial conditions, which we now call the butterfly effect. The idea that a butterfly flapping its wings in Brazil can set off a tornado in Texas.
And Margaret Hamilton was the one programming these machines when this realization was happening.
She was right there. She saw firsthand that in a complex system, a microscopic error doesn't just result in a microscopic mistake. It can cascade into total chaos.
That is a terrifying lesson to learn right before you go to work on a spaceship.
Yeah.
That must have stuck with her.
It absolutely did. It's a foundational experience. Because what you're saying is she learned firsthand that you cannot just hope the system holds together. You can't assume that small inputs will only have small outputs.
I can have massive, unpredictable outputs.
Precisely. She took that lesson, that systems are fragile and nonlinear, and she carried it with her for the rest of her career. And she did all this without ever taking a class in computer science.
Like, because they didn't exist.
Right. She said the field was so new that nobody could tell you that you were doing it wrong because nobody knew what right looked like yet. It was pure on-the-job training. You learned by doing and by, crashing the system and figuring out why.
So she leaves the weather lab, and in 1961, she moves to the Lincoln Lab at MIT to work on a project called SAGE.
The semi-automatic ground environment.
This sounds like the setting for a Dr. Strangelove movie.
It practically was. SAGE was a massive Cold War project. The U.S. military had built these colossal computers, the AMFS-Q7, which were the largest computers ever built. Each one took up an entire building, weighed 250 tons, and had something like 60,000 vacuum tubes.
Unbelievable. What was it for?
It was a networked air defense system. It took in radar data from all over North America, and its goal was to identify unfriendly aircraft.
Soviet bombers?
Exactly. The software was supposed to track incoming Soviet bombers and help guide interceptor jets to shoot them down before they reached American cities.
So if the weather software crashes, maybe you need an umbrella when you thought it would be sunny. If SAGE crashes?
We all die.
Okay, so the stakes were just a little bit higher.
The stakes were absolute. This was military-grade computing. It was the proving ground for high-reliability systems. But there is a specific story from her time at SAGE that I think perfectly illustrates who Margaret Hamilton was.
The Greek and Latin story.
Yes, this is a classic example of hazing in the engineering world. It was a sort of rite of passage.
Explain this to me, because it sounds like a complete waste of taxpayer money to be hazing people on a critical military defense project.
Well, think of it as a stress test. When a new programmer arrived, especially someone without a formal background, the veterans, The priesthood of coders would assign them a specific program to fix.
A trick program.
Exactly. It was known to be impossible. It was incredibly complex, convoluted logic. It had never run properly. And just to make it impossible to debug, the original author had written all the comments in the code in Greek and Latin.
So you open the file, and instead of instructions saying this function calculates altitude, it's literally all Greek to you.
Essentially, it was designed to be unreadable. The goal was to watch the new kid panic and fail. Nobody was supposed to be able to run it. It was just a way to humble the new recruits and, see who cracked under pressure.
So they hand this to Margaret. What does she do?
She doesn't panic, and she doesn't try to translate the Greek. She realizes the comments are a distraction. They are noise. She looks past them at the raw logic, the binary, the actual flow of the data through the machine.
She reverse engineered it.
Completely. She figured out what it was actually trying to do, and she found the flaws in the logic, and she fixed it.
She made it run. The impossible
She
part.
made it run. And then, for the ultimate flex,
Oh, I love this part.
when she got it to output the answers, she programmed it to print them out in Latin and Greek.
That is fantastic. That is the coding equivalent of catching a punch and hitting the other guy with his own hand.
It really is. But deeper than the joke, it established her reputation. It proved she wasn't just a coder. She was a systems thinker, a problem solver who couldn't be intimidated by complexity or, deliberate obfuscation.
She couldn't be bullied.
She could not. And that reputation is what put her on the radar for the Apollo program.
So let's go to the moon. It's around 1963 when she leaves SAGE, and then she joins the MIT Instrumentation Lab, which had the contract for the Apollo guidance system.
Right. And she said she saw an ad about the Apollo project and just found the idea of a moon program very exciting. It was the challenge of a lifetime.
She joins the lab.
Yeah.
And we need to be very clear about her role here because history tends to flatten these things. She wasn't just a programmer on the team.
No. She was the first programmer hired for the Apollo project at MIT, and obviously the first female programmer.
That is a lonely position to be in, the first person through the door.
Incredibly lonely. And she eventually rose to be the director of the software engineering division, leading a team of hundreds. But it was an uphill battle the entire way. Not just because of her gender, though that was certainly part of it, but because of her discipline.
Right, the hardware versus software culture war. This was a real thing.
It was a caste system. In the 1960s, engineering meant hardware. It meant building rockets, fuel pumps, circuits, metal. That was seen as real work.
Tangible things you could hold.
Exactly. Software. That was viewed as a secondary support task. It was seen as typing or something women did. It wasn't considered a science. It was almost like a craft.
Which is so ironic because the hardware is just a heavy, expensive paperweight without the software to tell it where to go and what to do.
Completely. But the hardware gurus didn't see it that way. They thought software was something you did at the end, like, painting the rocket. Hamilton realized early on that this attitude was incredibly dangerous.
Because if you treat it as an afterthought,
You get bugs. And in space, bugs kill people. There are no second chances. So she realized they needed more rigor, more discipline. They needed to be seen as equals to the hardware engineers.
so she starts fighting for legitimacy.
She did. She started using the term software engineering. She combined the words deliberately. She was making a statement. She was saying, we are not just typing. We are engineering a system with the same rigor, the same mathematical foundation, and the same discipline that you use to build a thruster.
And they laughed at her. Is that true?
It was an ongoing joke for a while. The sources say the hardware guys would kid her about her radical ideas. They thought it was hilarious that this woman from the typing pool wanted to call what she did engineering.
Unbelievable. Until they realized she was right.
Until the problems started getting so complex that they couldn't solve them without her team. There was a turning point, a specific meeting where a very respected hardware expert, one of the gods of the lab, finally stood up and admitted, essentially, she's right. What they are doing is engineering.
That must have been a huge moment.
Hamilton said it was. It was the moment they stopped being the help and started being partners in the mission.
And they had a lot of work to do. Her team was responsible for all the onboard in-flight software.
Everything. The command module software that got them to the moon and back, and the lunar module software for the landing itself. And later, they even did the software for the Skylab space station.
What was the key focus? What was the philosophy behind the software?
It was all about reliability, error detection, error recovery, and this concept of man-in-the-loop capabilities. How do the humans and the computer interact safely under extreme stress? That was her obsession.
Let's get into the weeds of that code then,
Yeah.
because this is Section 4, the architecture of survival. And I want to really understand this because the critique we've heard of other explanations is that they dumb it down too much.
Let's do it.
We need to talk about the asynchronous executive.
Yeah.
The previous explanation I've heard used a grocery store analogy, like checking out customers. But that feels too linear, too simple.
It is too linear. A grocery line is a queue. First come, first served. You wait your turn. The Apollo guidance computer could not afford to wait its turn. A better analogy is an emergency room doctor on a Saturday night.
Okay, I'm the doctor, the CPU.
You are the CPU. You have a patient with a sprained ankle. Let's call that job updating the astronaut's display. It's important the patient is in pain, but it's not life-threatening, so you're working on that.
I'm wrapping the ankle.
Then suddenly, the ambulance doors burst open, and a patient comes in on a stretcher with a massive heart attack. That job is fire the descent engine to stop us crashing into the moon.
Okay, that's a bit more important than the ankle.
Just a bit. In a normal linear computer, a grocery line computer, you'd have to finish taking the ankle before you could even look at the heart attack patient.
And the heart attack patient dies.
Exactly. The Eagle crashes. Hamilton's team, utilizing a brilliant design by a man named J. Halcombe Laning, built an asynchronous executive. It's a system based on interrupts and priorities.
So what does that mean in the ER?
The moment the heart attack patient arrives, the system literally freezes the ankle taping job mid-motion. It saves the state of that job, where the tape was, what you were thinking about, and it shoves it onto a back burner. Instantly, your entire brain, all your processing power, switches to the heart attack.
It's ruthless prioritization.
Ruthless and automatic. It creates a hierarchy of survival. The computer's programming had a list of jobs with priority ratings. Landing the vehicle was at the top. Everything else was below it. The computer knew, without being told, that keeping the ship upright was more important than talking to the astronaut.
But this introduces a new problem, right? The human interface. If the computer is jumping between tasks like that, how does the astronaut know what's happening?
That was the priority display challenge, and it was a huge focus for Hamilton. She designed routines where the computer could interrupt the astronauts, it could overwrite their screen if it had something urgent to say, but she realized this created a deadly new risk.
The man-in-the-loop problem. The human is too slow.
Exactly. Imagine you're the astronaut. You're about to press a button to say, turn on the landing radar. Your finger is moving toward the button. In that split second, the computer has a problem and decides to interrupt you. It changes the screen to a different menu, and now that same button means jettison the engine.
And my finger is already moving. I press the button.
And you've just jettisoned the engine you need to land because the computer changed the context faster than your brain could react.
That is a UI nightmare. How did she solve that?
With a surprisingly simple, low-tech human rule that was drilled into the astronauts during training. Count to 5.
Count to 5, that's it.
That was the core of it.
Yeah.
If a priority display pops up, if the screen changes unexpectedly, the rule was you take your hands off the controls and wait 5 seconds. Let the system settle. Make sure the switchover is complete before you touch anything.
It's a human buffer for a machine that's too fast.
Precisely. It's such a low-tech solution to a high-tech problem, but it was critical for preventing accidental disasters.
And then there is this feature that really saved the day on Apollo 11, the kill and recompute. This sounds aggressive.
It is the ultimate failsafe. Think about your laptop. If it freezes, what do?
I hold the power button down. It shuts off, I swear a bit, and I probably lose the document I was working on.
Right. In space, you cannot lose the document. You cannot lose your navigation alignment. If you restart from 0, you don't know where you are and you tumble. So Hamilton's team built a restart protection system.
How did it work?
The software was constantly taking snapshots of critical data, your position, your velocity, your orientation. It was saving these to protected areas of memory, like a series of safe checkpoints.
Like a save game in a video game.
That's a perfect analogy. It's a save game checkpoint.
Yeah.
If the software ever realized it was confused or getting corrupt data or about to crash, it wouldn't just blue screen. It was programmed to detect its own failure.
And then what?
It would perform a soft reboot. It would flush all the currently running lower priority tasks, reload the last known safe snapshot of critical data, and restart its processing from that safe point. And it could do all this in milliseconds.
So it was designed to fail and recover so fast the human might not even notice.
That was the goal. It was resilience by design. The system assumed failure could happen and was built to survive it.
And that brings us to the climax.
Yeah.
July 20th, 1969.
The ultimate test of that resilience. All those years of philosophical thinking and design choices are about to be put on trial.
We are back in the Eagle. 3 minutes to landing, and the alarms start.
Yeah.
12:01, 12:02.
Right. And to understand why this happened, we have to look at a piece of hardware called the rendezvous radar.
This is the radar they would use to find the mothership, the command module, if they had to abort the landing and fly back up, right?
Correct. It wasn't needed for the landing itself, but, and there is some debate here among historians and even the astronauts, but the prevailing theory from the engineers points to the switch position. The rendezvous radar switch was likely left in a mode that it shouldn't have been.
So it was on when it should have been off.
It's a little more complex than that. It was likely about the phasing of the power supply to the radar. Due to the switch position, the radar was receiving power that was out of phase with the computer's power supply. This created electrical interference.
Like static. Just noise.
Massive noise. The radar started sending thousands of phantom signals interrupts to the computer every second. It was essentially screaming, "Read me, read me, read me," at the CPU, demanding attention for a job that wasn't even important at that moment.
So the computer's trying to do the incredibly complex math for the descent, which is already hard, and suddenly it has this screaming child in the back seat kicking the chair over and over.
An excellent analogy. And then the straw that broke the camel's back. Buzz Aldrin, following his training, enters a command, 1668.
And what does command 1668 do?
It asks the computer to calculate and display the difference in altitude delta. Buzz wanted to double-check their height against what he was seeing out the window. A totally reasonable request. He had done it in simulations 100 times.
But the simulations didn't have the radar screaming in the background.
Exactly. The system was designed to handle a workload of about 85% of its total capacity to leave a safety margin. With the landing software running and now this constant barrage of radar interrupts, it was already pushed near its limit. When Aldrin asked for that extra display calculation, that was the 8th major task on a system built to handle 7, the demand on the CPU hit something like 115%.
Overload.
Total saturation. In any other computer of that era, probably any other computer on Earth at that moment, the system would have frozen, it would have crashed, the thrusters would have locked in their last position, the Eagle would have tumbled and crashed into the moon.
But it didn't freeze. The 12:01 alarm flashed.
And that alarm was the software talking. It was the system communicating its state. 12:01 meant executive overflow. The asynchronous executive, the ER doctor, looked at the list of tasks and said, "I have too much to do. I cannot process all of this in the time I have."
And here is where the genius of the design, the genius of Margaret Hamilton's philosophy, kicks in. It didn't quit.
No, it made a management decision. It looked at its prioritized list of jobs and said, updating Buzz Aldrin's display, that is low priority. Kill it. Servicing those screaming radar interrupts, not critical for landing. Kill it. Firing the descent engine to keep us from dying. Highest priority. Keep that running at all costs.
It effectively told the astronauts, "Shut up, I'm busy saving your life."
That is exactly what it did. It shed the load. It performed one of those soft reboots, a kill and recompute. Cleared the queue of low-priority junk, reloaded the last safe data, and kept the engines firing. And it did this multiple times during the final descent.
And in Houston, this is where the human element on the ground becomes critical. Jack Garman.
Jack Garman, a young NASA computer engineer, one of the backroom guys, he was looking at his console. He had a cheat sheet of all the possible error codes taped under the glass on his desk. Because Margaret Hamilton had insisted on rigorous testing and creating these very specific error definitions, Garman knew what 12:01 meant.
He knew it wasn't a death rattle.
Okay.
It wasn't the computer dying.
He knew it was the opposite. He knew it meant the computer was working perfectly. It was doing its job, shedding tasks to survive. So he yelled into the intercom to the flight director, "Go! Go!"
He gave them the go.
He gave them the go. If he hadn't understood that, if they had hesitated for even a few seconds, the mission rules were clear. They would have had to abort.
So Margaret Hamilton's code didn't just fly the ship. It gave mission control the information and the confidence to stay in the fight.
Hamilton wrote about this later in a letter to Datamation magazine. She said, and I'm paraphrasing, "If the computer hadn't recognized this problem and taken recovery action, I doubt if Apollo 11 would have been the successful moon landing it was."
It's just chilling to think about. The margin between a ticker tape parade and a global memorial service was a few lines of priority logic in a 72 kilobyte computer.
It really was. The whole mission balanced on that knife's edge.
So Apollo 11 lands. History is made. Margaret Hamilton is a legend inside the lab. But her story doesn't end in 1969. And this is the part that I think is most critical for our listeners, especially anyone working in tech or systems today. Section 6, the post-Apollo methodology.
This is where she pivots from being a heroic firefighter to being a fire marshal. She looked back at the Apollo project and realized that what they did was amazing, but it was also exhausting and, in a way, inefficient. They spent thousands and thousands of hours testing, finding bugs, and fixing them.
Error detection, finding the mistakes after they've been made.
Right, but she asked a deeper, more philosophical question. Why do we allow errors to exist in the first place?
That sounds like a utopian question. I mean, come on, code always has bugs. That's just a rule of the universe, right?
That's it. Or do we just accept that it does because that's how we've always done it? In 1976, she co-founded a company called Higher Order Software, or HOS, and later, in 1986, she founded Hamilton Technologies. And through these companies, she developed a concept she called Universal Systems Language, or USL.
Okay, let's unpack USL.
Yeah.
What is the core idea here? It sounds very abstract.
The core philosophy is development before the fact.
Development before the fact. Explain that to me.
Think about how we build almost all software today. You write some code, you compile it, you run it, it crashes, you say, oops. You go into the debugger, you find the mistake, and you patch it.
We call it agile. We iterate.
We iterate on failure. We test after the fact to find the errors we built in. Hamilton.
So it's like building a house with a blueprinting software that physically prevents you from putting a door where a load-bearing wall needs to be. It just won't let you draw it.
That is a perfect analogy. If the design is mathematically sound and complete, the code that is automatically generated from it will be reliable by definition. It moves the focus from software reliability, which is asking, is the code good, to system reliability, which asks, is the logic sound?
And when you look at the world today, I mean, you look at major software outages that take down airlines and banks, or the constant stream of security patches for our phones because of vulnerabilities, it feels like we went in the complete opposite direction of Hamilton's philosophy.
We absolutely did. The industry, by and large, chose speed over rigor. The mantra became move fast and break things. Hamilton's philosophy was move deliberately and break nothing.
And in a world where software is now controlling self-driving cars, pacemakers, and national power grids, her approach of development before the fact is arguably more relevant now than it was in 1969.
I believe so. It's a road not taken, or at least a road less traveled by the mainstream. But it's a standard we might need to return to as the stakes get higher and higher.
Let's look at her legacy, because for a long time she was a bit of a hidden figure outside of engineering circles. But the last decade has really seen her get her flowers, so to speak.
The recognition has been cascading, and it's been wonderful to see. In 2003, NASA gave her the Exceptional Space Act Award. And this is a great detail. It included a check for $37,200.
That seems oddly specific. Why that amount?
At the time, it was the largest individual financial award NASA had ever given to anyone in its history. It was their way of saying, you know, we know you, and this is the biggest thank you we're allowed to give.
That's incredible. And then the big one in 2016.
The Presidential Medal of Freedom, awarded by President Obama. He draped it around her neck, and that is the highest civilian honor in the United States. And the citation explicitly credited her with creating the software concepts that allowed for the moon landing.
She also got into the National Aviation Hall of Fame and became a Computer History Museum fellow. But I have to ask about the pop culture stuff, because you know you've really made it when you're a Lego.
Oh, absolutely. The Women of NASA Lego set.
Yeah.
It's fantastic. It features her in her 1960s outfit, and it actually includes a tiny Lego stack of the code books next to her.
Recreating that iconic photo.
Yes. And there was another beautiful tribute by Google back in 2019 for the 50th anniversary of the landing. They went to the Ivanpah solar power facility, you know, that massive array of mirrors in the Mojave Desert.
The one that looks like a sci-fi power plant.
That's the one. They programmed over 100,000 of those mirrors to reflect the moonlight, literally moonlight, to create a giant portrait of Margaret Hamilton on the landscape, visible from above.
A portrait drawn in moonlight. That is poetry.
It's perfect. And for the TV fans out there, if you watch the show For All Mankind on Apple TV plus Bank, the character of Margot Madison is heavily inspired by her. The glasses, the intense drive, the sheer brilliance.
But beyond the Legos and the medals, her biggest victory, I think, has to be that name. Software engineering.
It really is. In 2018, the IE Software Journal celebrated the 50th anniversary of the discipline. They were celebrating the very field she named. It went from being a joke that hardware guys laughed at to being the dominant, most important industry of the 21st century.
She hired the sheriffs for the Wild West.
She did. She proved that code wasn't magic and it wasn't just typing. She proved it was an engineering discipline that could be trusted with human lives.
So to wrap this all up, Margaret Hamilton didn't just write code. She created the entire environment, the philosophy, where code could survive chaos. From that trick Greek and Latin program where she outsmarted the hazing ritual, to the moment she taught a computer to ignore a screaming radar and land on the moon, she consistently solved the impossible.
And she did it by sticking to her guns, by trusting her logic and her rigor when the rest of the world told her she was just support staff.
So here's a final thought for you to chew on. We live in a world of beta tests and move fast and break things. We accept that our apps will crash. We accept that our smart fridges might need a reboot. Margaret Hamilton's philosophy was that errors are not inevitable. They are a failure of design. As we build ever more complex AI and autonomous systems that will hold our lives in their digital hands, why have we moved so far away from the failure's not an option rigor of Apollo? Maybe it's time we stopped just fixing bugs and really started preventing them from ever being born.
Development before the fact. It's a powerful idea whose time may have come again.
If you haven't seen that photo of her with a stack of code, go Google it right now. It is the definition of iconic. Thanks for taking this deep dive with us.
It was a pleasure.
See you next time.